welcome to the frontiers of parameterized complexity. Our speaker today is Ariel Kulik, who will speak on his new ways of analyzing branching algorithms. Please, Ariel. You have to switch on your microphone.
Yes, can you hear me now?
Yes, perfect, please.
Great. Okay, so this is joint work with my PhD supervisor, Hadas Shechnai. What we're going to have is a fairly long introduction, which will present the main algorithmic idea, along with the mathematical problem we needed to solve in order to understand the running times of our algorithms. Then we will go over the main results of the paper. Then, depending on time, we will either discuss a bit of the technical solution for recurrences or about how to obtain a faster algorithm, and we will have a short summary. So we're going to speak about vertex cover. So given an undirected graph, a subset S of vertices is a cover or a vertex cover if for every edge UV in the graph, S intersect U and V. That is, there is a non-empty intersection between S and UV. So here we have a small graph, and these two vertices form cover. And the problem can be cast as an optimization problem in which we want to find a cover S with minimal number of vertices. It can be also cast as a parameterized problem in which we want to determine whether a graph G has a cover S with K or less vertices. So there's a very simple polynomial time 2 approximation for the problem. And under the unique games conjecture, there is no 2 minus epsilon approximation. And the problem is known to be in FPT. And the best running time of a parameterized approximation for the problem is, parameterized algorithm for the problem is 1.273 to the power of K. And it's known that there is no sub-exponential time algorithm under ETH. And the problem serves as a testbed for techniques in parameterized complexity, which is essentially what we did. We're going to discuss parameterized approximation. So for an alpha between 1 and 2, we say an algorithm is a parameterized alpha approximation for vertex cover if, given a graph G, which has a cover of size K, the algorithm returns a cover of size alpha K. And we require the running time to be in FPT, but because vertex cover is already in FPT, what we are really looking for is a trade-off. We want that as we increase alpha, as we allow the approximation to be worse in some sense, we want to reduce the running time. And vertex cover has been studied from this perspective before. And one result provides a complete trade-off. That is, for every alpha between 1 and 2, there is 1.2378 to the power of 2 minus alpha, all of this to the power of K, parameterized alpha approximation. And the base of the exponent for these algorithms as a function of the approximation ratio of alpha can be seen here by the blue line. And this result can be obtained using some approximate preprocessing. Other works designed branching algorithms which are dedicated to derive approximate solutions. Those are faster. So a good example is a 1.5 approximation in time of 1.0883 to the power of K. And the base of the exponent as a function of alpha for these algorithms, so those are due to Brankovic and Fernau, are the black dots in this graph. And what we got is this red line, this new trade-off between the running time and the approximation ratio, which is some substantial improvement for a variety of approximation ratios. So we will start with presenting the main idea of the technique. And we will start with a very simple algorithm, one of the simplest parameterized algorithm for vertex cover, which goes as follows. You just pick an edge U and V, and you branch over the two options, which are either U is in the cover or V is in the cover, and you repeat for K times. So this is a simple 2 to the power of K algorithm. We can see its branching tree illustrated here. And it can be viewed as if there is one good leaf we're looking for in this branching tree, and we simply go over the leaves, looking for this specific leaf, which represent a cover. And the first thing we can think about is that, well, we're looking for an approximate solutions, so we can repeat this process for k+1 times. That is, we will look for solutions of size k+1, given that the input graph has a solution, has a cover of size k. And we can look at the resulting branching tree. Now, for sure, this branching tree has twice the number of leaves because we added a new layer to the graph. But the number of good leaves, the number of leaves which represent a solution, has now increased to be k+2. And the reason for that is that every time the algorithm branches over two options, one of them is a correct options. And as long as we get from the root to one of the leaves, while only making one incorrect choice, we will end up with a cover, because we will add at least k vertices from the correct solution to the cover. So essentially, we increased the number of good leaves faster than we increased the number of leaves at all. And of course, it doesn't make any sense now to go over the leaves one by one, because there are more leaves. But this is where randomization can come into play. And what we can do is to use some randomized branching variant. That is, instead of branching over the two options, which are that I either U is in the cover or B is in the cover, we can add U to the cover with probability F, and with probability half, we add the vertex V to the cover. And we can repeat this process alpha k times. That is, we're looking for a solution of size alpha k. And for sure, this algorithm is a polynomial time algorithm. We don't actually branch over two options. We select one of them at random. And the real question is, what is the probability that this algorithm finds a cover? For sure, if it finds cover, it is a cover of size alpha k. So we want to understand what is the probability that this randomized algorithm finds a cover. And apparently, it's fairly easy to analyze this algorithm. So we can denote by xn, or use xn as a random indicator, such that xn equals to 1 if the nth vertex selected to the solution is in an optimal cover, and xn equals to 0 other ones. And because either one of the endpoints of every edge u and v must be in an optimal cover, it also the probability of xn to be 1, even if we condition it on the previous indicators, is at least half. Therefore, the probability that we found a cover is at least the probability that we added k, that we selected the right vertex k times, that is x12 plus x alpha k is at least k. And this in turn can be lower bounded by the probability that a binomial random variable with alpha k trials and probability half is at least k by this probability. And now this is a standard probability, and we can use some standard tail lower bound for it. So we can lower bound it by 1 over alpha k plus 1 square times the exponent of alpha, the divergence of 1 over alpha and half, all of this to the power of minus alpha. The divergence here is the Kulik-Libler divergence. And just in order to simplify, we can write this exponent of alpha of the divergence as C alpha. So we can lower bound the success probability of the algorithm by 1 over some polynomial factor times C alpha to the power of minus K. And this lower bound, this tail bound is a standard bound, but one of the easy ways to derive it is using the method of types, which will play a central role in the paper, in the analysis we will do later. So what we can do is that we have some lower bound over the success probability of the algorithm, So we can repeat the algorithm for the inverse times of the lower bounds. That is, we will run this randomized branching algorithm for alpha k plus 1 square times C alpha to the power of k times. Therefore, if the input graph G has a cover of size k, this algorithm has a constant probability, or in constant probability, the algorithm finds a cover of size alpha k. So in essence, this is an alpha approximation algorithm, and its running time is dominated by C alpha to the power of k. So the next thing to do is to evaluate C alpha, or to draw it. So we have here C alpha as a function of alpha. The approximation, it's the orange to yellow line. And for example, for alpha equals to 1.5, the running time is 1.0887 to the power of k, which only differs from the previous best result by this 7, by the 4th digit. And that is, it nearly matches the running time of the best previously known result. And what we can see is that for alpha equals to 1, that is, if we look for an exact algorithm, it has the same running time as the original algorithm we started for. And the main benefit we have is that as alpha increases, the running time significantly decreases. Okay, so before I continue, I'll see if there are questions. Don't have the chat here. Okay. Any questions, something? Okay. Okay, so what we have so far is we took some very basic algorithm for vertex cover. We used randomized branching, and we obtained some result for parameterized approximation, which nearly matches the state of art. And the natural thing to do is to think about, well, what happens if we take some more sophisticated algorithm, faster algorithm for vertex cover, and we repeat the same process. So for example, we can take another algorithm. It's still a textbook algorithm. It has a runtime of 1.46 to the power of k, and it uses the following logic. If there is a vertex V in the graph with degree 3 or more, the algorithm branches over two options, which is that either V is in the cover, or if V is not in the cover, then the neighbors of V are in the cover. And otherwise, if there is no vertex of degree 3 or more, the maximal degree in the graph is at most 2. And for such graph, a minimum vertex cover can be found in polynomial time. Now, the running time of this algorithm is dominated by the recurrence P of k equals to P of k minus 1 plus P of k minus 3. And there is a standard solution for it, and you can obtain the running time. Okay, so we can, but as I said, what we will try to do is to convert it into a randomized algorithm in order to obtain an approximate solution. So what we can do is we can fix some gamma between 0 and 1 and replace the branching by a randomized selection. That is, if there is a vertex V with degree 3 or more, with probability gamma, we will add V to the cover, and with probability 1 minus gamma, we will add 3 of its neighbors to the cover. And if there are no vertices of degree 3 or more, we just find a minimal cover. Now, this is for sure a polynomial time algorithm, and it certainly finds cover. So the only question is, what is the probability that this algorithm returns cover of size alpha k? And what we can do is we can denote by capital P of B and k the minimal probability that the algorithm returns a cover with at most B vertices. We will refer to this B as our budget, given that the input graph has a cover of k or less vertices, and k will be our parameter. Now, I will write this very long recurrence here, and my claim is that this small p of b and k, defined by this recurrence, lower bounds this capital P of b and k. So let's take a look at this recurrence. So P of B and K is the minimum over two terms. And the first term deals with the case in which the vertex V is in an optimal cover. So if the vertex is in an optimal cover, with probability gamma, the algorithm selects it to the cover. So in this case, the budget decreases by 1 because a vertex was added to the cover, but also the minimal vertex cover size decreases by 1 because we selected a vertex from the optimal cover into the solution. And with probability 1 minus gamma, the algorithm selects three of the neighbors of V to the cover. So the budget decreases by 1, but the minimum vertex cover size does not necessarily decrease at all. And the second line deals with the case in which the neighbors of V are in the optimal cover. So in this case, the algorithm selects V to the cover with probability gamma. And in this case, the budget decreases by 1. The parameter does not decrease at all because V is not in an optimal cover. And with probability 1 minus gamma, the algorithm selects 3 of V's neighbors to the cover. Because V is not in an optimal cover, all of them must be in an optimal cover. So the budget decreases by 3 and the parameter decreases by 3. And the initial conditions are fairly simple. We cannot find a cover of negative size. So if B is smaller than 0, P of B in K is 0. And if the minimal vertex cover size is 0 and our budget is non-negative, for sure the algorithm finds a cover within the budget. Now, it's not a formal proof that this capital P of B and K lower bounds P of B and K, but it provides the intuition for this claim. Okay, so what can we do with it? So we have this recurrence, and we can note that for any fixed or for not fixed, for any B and K, we can compute P of B and K using a dynamic programming. So we can evaluate its value. And then we can execute the randomized branching algorithm for 1 over P of alpha K and K times. And the result is an alpha approximation with a constant success probability. So up to the randomization factor, this is a parameterized alpha approximation algorithm, and its running time is dominated by this argument by 1 over P of alpha K and K. So in order to understand the running time, what we want to find is some C, hopefully we want to find some constant C, such that P of alpha K and K is approximately C to the power of minus K. Or it can be formally stated as we want to find the limit of K goes to infinity of 1 over K log P of alpha K and K. And with some surprise, we did not find a solution for this recurrence. So there was no previous solution, and it essentially became the focus of the work. Okay. Any questions before I continue? You're all very quiet. It's very strange. Okay, so what are the main results? So essentially what we did is we generalized this specific recurrence into a family of recurrence relations, and we provided a solution for the recurrences. So we have some formula which evaluates the asymptotic behavior of these recurrences, and we used this solution to analyze the running time of randomized branching algorithm of yes, for the parameterized approximation algorithms, for vertex cover and 318 set, and we obtained significant improvement over the running time of previous algorithms. And the result is done by using randomized branching and this formula for understanding the asymptotics of the recurrences. Okay, so let's start by generalizing the recurrence. So we have here P of, the recurrence we already have is P of B and K equals to the minimum of those two terms. And each term is some coefficient times P of B minus some number and K minus some number plus some coefficient times P of B minus some number and K. Here it's minus 0, but it's also minus some number. And the second term looks just the same up to the exact value. So we can use some more abstract notation in which the formula is that P of B and K equals to the minimum of some coefficient gamma 1, 1 times P of B minus B1, 1 and K minus K1, 1. And we can continue in the same way, and we can write those two terms in this way. And we have here the values of the vectors. And the next, so we have some more abstract way of viewing this recurrence. The next thing we can think about is that each of the terms here consists of only two summands, and we can make some more take a more general view in which the minimum is taken over two terms, but each term is the sum of some R number of summands. So the first term, for example, is the sum over I goes from 1 to R1, the coefficient gamma 1i times P minus B1i and K minus K1i, and the same goes for the second term. And the last thing we can think about is that we don't want to restrict ourselves just to two terms. We can have an arbitrary number of terms, so we will have some n terms, and the minimum will be taken over all the values of j from 1 to n, and the sum of I from 1 to rj, gamma ji times P of B minus Bji and K minus Kji. And those are essentially the recurrences we solved. We considered functions P which satisfy this recurrence with the same initial conditions we had before, that is P of B and K 0 for negative B, and P of B and 0 is 1 for non-negative B. And we have some basic requirement. We want the number of terms to be a natural number, and we want that each term will have some natural number of summands. We want the coefficient vectors to be of positive numbers which sum into 1, and we want the vectors kj and bj to be of natural numbers. And we will view this tuple of gamma j, bj, kj as the term that is the sum of I goes 1 to rj, gamma ji times P of bji and K minus Kji. And I have an asterisk here because there is some additional technical condition which you can look at the paper. And what the main theorem states is the following. For every alpha and term gamma j, bj, and kj, we define an alpha branching number, mj, which is some function f of alpha, gamma j, bj, and kj. I'm not going to write f here, but the important thing, at least not at the moment, the important thing is that f is some solution for a quasi-convex minimization problem, and it can be numerically computed. And what the main theorem states is that the limit of 1 over k log P of alpha k and k is minus the maximal branching number. Or alternatively, it means that P of alpha k and k is approximately the exponent of the maximal branching number to the power of minus k. And it means two things. The first is that we have a solution, we have some formula, and we can compute the asymptotics of such recurrence relations. And the second thing is that we have some structure. That is, we know that the asymptotic of the recurrence is dominated by one of the terms for which the branching number is maximal. And this, in some point, will serve as a guidance for developing the algorithms. And it's very simple it's very similar in some sense to standard recurrences which have branching numbers. Okay, so let's see how this theorem can be used. So recall that we had this recurrence before, P of bk, and it's just the recurrence we saw before. And it's not well defined because gamma is unknown. We didn't set any value for it. So I can tell you that gamma equals to 0.7463 is a good number. And what we have is that by the theorem, the limit of 1 over k log P of 1.5 k and k is minus the maximum over the branching number of the first term and the branching number of the second term. And as I said, we can plug the values of the terms into a computer, and we can get the value of the branching numbers. So here you can do it, and we'll get a number. We'll get that this is approximately 0.04271. I omitted some digits here. And what it means is that P of 1.5 k and k is approximately 1.04364 to the power of minus k. Okay, but as you recall, we already had found a 1.5 approximation algorithm, but we didn't know its running time. All we knew is that the running time is 1 over P of 1.5 k and k. But now we have a formula and we can compute it. We know that the running time is 1.04364 to the power of k, which is by now a significant improvement over the previous best result. And the last thing is that you may wonder where this gamma came from. And the answer is that the problem of finding a gamma for which the maximal branching number is minimal is also quasi-convex. So we can just plug it as well into a computer program and we get a solution for an optimal value of gamma. And what we did in the paper is we used this solution for the recurrences to find parameterized approximation algorithm for vertex cover. And this graph, it's the same as one seen before. It presents the base of the exponent of the running time of the algorithms as a function of the approximation ratio. And some nice examples are 1.5 approximation in time of 1.017 to the power of k. This is actually a simple variant of the algorithm which we've just seen, and a 1.1 approximation in time of 1.16 to the power of k. And we also have additional results for three thin sets. Okay, and some related work about recurrences. So recurrences in a single variable can be easily solved. It's taught in introductory courses. And the only similar work we found is a work by Epstein from 2006, which considered a different class of multivariate relations, and it is commonly used in measure and conquer algorithms. Okay, any questions before I continue? Something in the chat. Okay. So I want to give you some insight into the way we obtain the formula for recurrences. And I encountered two problems when I tried to put it into the slides. The first is that the recurrences are abstract. We found a solution for a mathematical problem, and it's not an algorithmic problem, and it's very hard to relate to. And the second thing is that the analysis is complicated. It's a technical analysis and it's a long one. And so in order to overcome those problems, I will try to do two things. The first is that instead of providing an analysis for recurrences, I will provide an analysis for the algorithm we just saw. It will be less abstract and more concrete. And the second thing is that I will make very strong assumptions to make the analysis easier, while I will still introduce the main ideas in the same time. So we'll get back to our algorithm. It's the same one. We fix some gamma and we pick a vertex V with degree 3 or more, and we add it to the cover with probability gamma. And with probability 1 minus gamma, we add its neighbors to the cover. And our assumption will be that the vertex V is always in a minimal vertex cover. That is, the algorithm always wants to choose V. It doesn't know it needs to choose V all the time, but this is the right option for it. And we will also assume this process is essentially infinite. So what we're looking for is to find P of B and K. That's the probability that this algorithm finds a cover of size B or less, assuming such a graph has a cover of size K or less. And we will define a random process to this end. We will define yn of n goes from 1 to infinity, such that yn equals to 1 if at the end step of the algorithm selected V, and otherwise we will have yn equals to 2. So what we have is that the probability of yn to be 1 is gamma, and the probability of yn to be 2 is 1 minus gamma. And we can express this capital P of B and K using those y's using a probability. What we have is a probability is that P of 1.5 k and k is the probability that in some point during the execution of the algorithm that we will have some n, such that by the nth step, the algorithm only added at most 1.5k vertices to the solution. And at the same time, it added at least k correct vertices to the solution. That it added at least k vertices from the optimal solution to the solution the algorithm generates. And it can be written that as the sum of L goes from 1 to n of B of YL is at most 1.5k. Here, B of 1 is 1. It's the number of vertices we add to the cover if Y is 1. And B2 is 3. That is the number of vertices we add to the cover if Y is 2. And we wanted the sum, the bound over the number of correct vertices added to the solution is the sum of L goes from 1 to n, k YL is at least k, where k1 is 1, because if y is 1, we added exactly one vertex from the optimal solution to the solution of the algorithm. And if YL equals to 2, we do not, then K2 equals to 0, we do not add any correct vertex to the solution. We do not decrease the minimal vertex cover size. And once we can formulate our problem in terms of probability and event, we can use the method of types. So what I will present is some degenerate definition of types. So given a vector A1 to AN with entries in 1 and 2, we say that the type of A1 to AN, T of A1 to AN, is a two-dimensional vector, T1 and T2, such that Ti is the frequency of I in A1 to AN, that is the number of indices L, such that AL equals to I, divided by N. And we have an example here, that is the type of 1, 1, 1, 2, 2, 1 is 4 over 6 and 2 over 6. This is because the first entry is the relative frequency of 1, and 1 appears here 4 times. So its relative frequency is 4 over 6. And the second entry is 2 over 6 because it's the relative frequency of 2, and it appears 2 times out of 6. So it's 2 over 6. And one of the main results within the method of types is Sanov theorem. And in the setting of Sanov theorem, what we have is a set Q of distributions. That is, each vectoring, the set Q is a set of vectors, each of 2 dimensions of non-negative numbers. And the entries of each vector sum into 1. We will also use this gamma bar to denote the vector of gamma in 1 minus gamma. And Sanov's theorem states the following: the probability of y1 to yn, so that is the random variables we just defined, to be in Q, the probability that the type of y1 to yn to be in Q is approximately the exponent of minus nc, where c is the minimum over all the points Q in the set Q of the divergence of Q and the vector gamma. And this can be formally stated as this limit. And what it means is that the probability that the type of y1 to yn is in some set Q is dominated by a point in the set Q, which is the nearest point to gamma, when we take the distance using D, the Kulik-Label divergence. And essentially what it means is that if we can express our event in terms of types, then we have some efficient way to evaluate its probability. Okay, so let's do it. Let's try to express our event in terms of types, because our event is essentially what is the probability that there is some n, that is a point in the execution of the algorithm, by which we added at most 1.5k vertices to the solution, and at least k of them were correct. And this can be formulated as the probability that there is some n, such that the type of y1 to yn fulfills some constraint. What is this constraint? Is that each time we have YL equals to 1, we added a single vertex to the solution. So the number of times we add YL equals to 1 is n times T1. And we multiply it by V1. And then we add the number of times we had YL equals to 2. And each time this happened, we added 3 vertices to the solution. And we want the sum of these two numbers to be at most 1.5K. And we can do the same with the number of vertices added to the correct solution, because each time we add a vertex which select V, we assume it is a correct vertex. We reduce the minimal cover size by 1. So we can write this in terms of types, and we can just play with the formula. So what we have is we want to evaluate the probability that there is some n such that the type of y1 to yn fulfills 2 linear constraints, and we can write it in terms of set. We want to write these 2 constraints as some set. So what we really want is to evaluate the probability that there is some n such that the type of y1 to yn is q of k over n, where q of k over n is defined by this set. So I don't want to dive too deeply into the formulas here, but the important take here is that we're able to express this event in terms of types. We want to express it as the probability that there is some n, so that the type of y1 to yn is in some set. And this is close to the form of Sum theorem, but not exactly. So what we do is we basically guess the solution. We will look for some beta star and q star, which minimize 1 over beta and the divergence of q and gamma. And because we're looking for the event that there is some n that fulfills some property, we can lower bound it by focusing on a specific n, which is k over beta star. We will ignore the problem that it might not be an integer. So we can lower bound this event by the probabilities that the type of y1 to y of k over beta star is in q of beta star. And by Sum theorem, we know that the probability of this event is roughly the exponent of minus k over beta star, the divergence of q star and gamma. And it's not hard to find a matching upper bound. But essentially, if we found a lower bound and an upper bound, we basically got a formula for p of 1.5k and k. So, and the formula is those b star and q star, and they are indeed a solution for some optimization problem. Okay, so of course, this provided some of the ideas we have to solve the recurrences under some very strong assumption, and we only analyzed the algorithm. So what we have in the paper is a more complicated random process. Though the random process we analyzed is simply the algorithm. We just prove that the algorithm is essentially equivalent to the recurrence. Of course, it needs to involve all the terms. That is, we cannot assume that the vertex V is always in an optimal solution. And once this happens, we cannot apply Sum theorem directly. And the good thing was that some of the properties of types carry over to this new process, and we're able to provide a variant in some sense of Sum theorem. So after this heavy mathematical part, we will have some very nice, light and easy algorithmic part in which we will show some simple idea on how to improve the running time of the algorithm we already seen. By the way, are there any questions right now? Questions, something? Okay. So as you recall, we showed a 1.5 approximation for vertex cover, which has a running time of 1.0437 to the power of k. And what it did is that with probability gamma, it selected the vertex V to the cover. And with probability 1 minus gamma, it selects 3 of the neighbors of V to the cover. And we showed that the running time of the algorithm can be evaluated using the following recurrence. And what we will do is we will try to use some more refined analysis, and we will focus on the case in which the vertex V is in a minimal cover and it has exactly 3 neighbors. And there are 2 possible scenarios in this case. One of them is that the vertex V is indeed in an optimal cover. Sorry, so we assume it's an optimal cover, and there was one scenario in which the algorithm selects V to the cover. So in this case, we added a vertex from an optimal solution, so the parameter decreases by 1. The other option is that the algorithm selects the neighbors of V to the cover. And what I claim is that in this case, the parameter also decreases by 1. And the reason is that if we select the neighbors of V to the cover, then all the edges adjacent to V are removed from the graph. Therefore, V does not cover any new vertices, and it can be removed any edges, and it can be removed from the cover. So the claim is that in both cases, the parameter decreases by 1. And we can use this to derive some better algorithm. And it will be very similar to the previous algorithm. It will try to find a vertex V with at least 3 neighbors. If there is no such vertex, it will find a minimum vertex cover in polynomial time. And it will have some cases within it. The first case is that the vertex V is of degree at least 3. And in this case, with probability gamma 3, we will add V to the cover, and with probability 1 minus gamma 3, we will add the neighbors of V to the cover. And the other case is that the vertex V has degree greater than 3, that is at least 4. So we will have some small distinction in this case. With probability gamma 4, we will add V to the cover, and with probability 1 minus gamma 4, we will add 4 of the neighbors of V to the cover. And what I claim is that the probability that this algorithm finds a cover of size P or less is this recurrence, which has 4 terms. And let's just look at the first term, for example. It deals with the case that the vertex V is in an optimal cover and it has degree of exactly 3. So with probability gamma 3, the algorithm selects it to the cover. In this case, the budget decreases by 1 and the parameter decreases by 1. And with probability 1 minus gamma 3, the algorithm selects 3 of the neighbors of V, that are exactly 3, to the cover. So the budget decreases by 1, but also the parameter decreases by 1 by the previous argument. And the second term deals with the case that the vertex V is not in an optimal cover and its degree is exactly 3. So in this case, the algorithm selects the vertex to the cover with probability gamma 3. The budget decreases by 1, but the parameter does not decrease. And with probability 1 minus gamma 3, it selects the neighbors of V to the cover. So they are indeed in an optimal cover because we assumed V is not in an optimal cover. So the budget decreases by 3 and the parameter also decreases by 3. And the next 2 terms are just the same analysis, only for the case that the vertex V is of degree 4 or more. Now, what we can do is use the main theorem to evaluate the asymptotics of P of 1.5 k and k. We can along the way also find the optimal values for gamma 3 and gamma 4. And what we will get is that P of 1.5 k and k is roughly 1.035 to the power of minus k. And we can use the following algorithm. We can repeat this randomized branching algorithm for the inverse of P of 1.5 k and k times. And so, therefore, we will get a 1.5 approximation with a constant probability. And the running time will be roughly 1.035 to the power of k, which is some nice improvement over the previous algorithm. And this idea can be generalized. We can have a more and more refined analysis. We can have gamma 3, gamma 4, gamma 5, and so on. And this results nearly in the optimal, and not the optimal, the best algorithm we have for 1.5 approximation. And the interesting thing to look at here is that while in classic branching algorithms, there is a right option, a correct option, and an incorrect option, and the algorithm and the analysis only focuses on the case that the algorithm chose the correct option, And in randomized branching algorithm, you also care about what happens if the algorithm took the wrong branching option. Okay, you are all very quiet. It's frustrating. So we will only have a summary. What we had in this paper is an analysis of recurrence relations with two variables. The analysis used the method of types. We got a simple formula for the recurrences, and we got some in-depth understanding for the behavior of these recurrences because of the branching numbers. And we used the analysis along with randomized branching to obtain faster parameterized approximation algorithms for vertex cover and 3D set. And the algorithms are fairly simple, and they obtain a significant improvement over the running time of previous algorithms. And that's it. Thank you.
Thank you very much, Ariel. We have time for questions.
Vedor, can I maybe ask a quick question?
Yes, I can.
So thanks very much for the nice talk. Your algorithms are currently randomized. Is it easy to think of de-randomized versions of this?
It's interesting to think about de-randomized versions. I don't know how to do it. It's an interesting question, but I don't have a solution for it. I don't have a good answer, at least.
So did you try to make an algorithm for feedback vertex set?
So it's very easy to get a naive algorithm for feedback vertex set. So if we take there's a very simple algorithm which finds a randomized algorithm for feedback vertex set in times of 4 to the power of k. And you can use it to derive parameterized approximation fairly easily. But if you try to get some interesting results, you need to read the current literature about parameterized algorithm for feedback vertex set, and I still didn't get to it. So it seems possible to get some simple algorithm, and getting a sophisticated algorithm requires more work. And the conclusion I have from this work is that thinking results in better algorithms. And I mean, if you put some effort in it, you get better algorithms. And I still didn't get there.
Yeah. Okay. So more questions, please. Well, if not, then thank you very much, Ariel. So yes.
Thank you.
And see all of you in 2 weeks. Yeah. Bye. Oh, wait a second. Yes, there are thanks in the chat. Yes.
Okay.
Yeah. Okay. Yeah. Bye.
Bye-bye.